Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. Last one of this year, I think. All right, we seem to have quite a few questions, including some very long ones here, saved up. First question I see here is from Sarv. What is computation? How does matter go from randomly moving particles to something that starts computing? It's an interesting question. As far as I'm concerned, computation is the application of definite rules. So you specify rules by which a system operates, and then as you follow those rules, you're doing a computation. Now, sometimes that computation is one where we humans say, oh yeah, we want to know the answer. Sometimes it's just a computation that's happening in the wild, just applying some set of rules without sort of any kind of sense of purpose to the computation. Now, it's usually the case that even if you have something where you have just defined its rules and you look at what it does, you can say, look, it did this thing, it's achieved this purpose. It ran, it produced this whole pattern of output. That was its purpose. It's very slippery to distinguish kind of mechanism for something from the purpose of the thing, because you can always say, whatever it did, that's its purpose. And you can perhaps identify some special feature of what it did and say, now we've identified its purpose, it is operating for that purpose. But as far as I'm concerned, whenever you have definite rules, the working out of what those rules do is the story of computation. Now, the thing that's tricky is you might have thought, well, you have some very simple set of rules. It'll do something only very simple. It'll never be able to do any sophisticated computation. To do a sophisticated computation, you'll need sophisticated rules like the ones that are defined for the machine code of a typical microprocessor or something. But the big discovery, I guess, I made in the early 80s, well, kind of really understood it by the beginning of the 90s, is this thing that I call the principle of computational equivalence that says for almost any set of rules, so long as their behavior isn't trivial, isn't really simple, like just repetitive, for example, that the behavior you get will be capable of showing arbitrarily sophisticated computations, or at least computations that are as sophisticated as anything that can be executed, for example, in our physical universe. So that's a non-trivial fact about the world. We've sort of, over the years, we've gotten more and more evidence for the principle of computational equivalence, more and more cases where yes, that very simple system where the only thing where it's sort of the simplest of its kind, simplest cellular automaton, simplest Turing machine, whatever, did turn out to be provably capable of sort of as sophisticated computation as anything, at least if you started off with the right kind of pattern of initial conditions, so to speak. So to say that something is computing, you might say, well, it's like you have a computer. You started off with some program. It runs that program. It does something. If you started off with a different program, it would do something different. The big fact about computers, universal computers, is that you can feed in a program to make any computation you want happen. What does that really mean? Well, you could take different computers with different intrinsic instructions, different machine code instructions, and you could say, well, I've got this one computer and it runs this set of operations defined by its machine code instructions. I've got this other computer, it runs these different computations defined by its machine code instructions. But the big fact that got first realized kind of in the 1930s and then sort of gradually became more widely understood, and then my own efforts sort of extended that in a certain way in the 1980s that I'll describe. But the big point about universal computation is that once you have something which can act as a universal computer, it doesn't matter that its instruction set is this particular thing. It can emulate any other instruction set of any other computer. You're effectively making an interpreter which says, okay, I want to behave like computer B, but I'm computer A. I can encode a program for computer A that makes computer A behave like computer B for any computer B. And so that's kind of what makes computation non-trivial is that as soon as you get to a certain level of kind of rules, you immediately have the situation that you can compute anything that any computer in our physical universe can compute. Now, the question is that thing that it's computing something that we humans would recognize as, oh, that's a computation I wanted to do? Absolutely not. Most computations that are done kind of in the wild by systems operating according to rules, where the rules are sufficient to be able to do any computation, most actual computations that are done will be computations that we humans don't have any particular interpretation for. We don't have any kind of narrative story about, oh, this computation is doing this particular thing. So this question of when do kind of just random particles bouncing around start doing computations, I think a basic definition of that is when they reach this point, this computational equivalence point, this point of computation universality, when it is the case that the set of things you're looking at least with appropriate initial conditions, with appropriate sort of initial setup, can do any computation you want, then for sure you can think of that system as sort of doing computation, even though it's computation in the wild that doesn't yet have a human interpretation. Now, it gets a little trickier because this question of whether the computations you do are given a particular initial condition and a particular set of rules, a definite thing will happen. It's this idea of universal computation that you can kind of emulate any other computer when the other computer is doing anything that the other computer can do. That idea of emulation relies on the idea that you can choose, you can look at lots of different possible initial conditions. You can set up an initial condition which has the property that it will emulate anything that that other computer can do, where different things that other computer can do are emulated by different initial conditions on the universal computer. Now, this principle of computational equivalence of mine goes a bit further than that, and it starts talking about what happens with particular initial conditions, not running over the set of all possible initial conditions, but that the computations that get done, even with particular initial conditions, are sophisticated computations. And to really get into that, one has to start talking about the idea of computational irreducibility, the idea that even if you look at a particular computation, you can ask the question, did you really need to do that computation step by step? Or is there some other computer that can come in and kind of jump ahead and say, oh, I know the answer without going through all the steps? It's the fact that there is irreducible computation that leads to sort of the fact that there is kind of a hard notion of computation that's going on there. And so what does it mean for there to be computation happening in things? It's really, in some sense, it means those things are, you can think of them as kind of mind-like in a certain sense, in the sense that you can say, like, our minds are trying to sort of do things like work out what will happen. And we do that by kind of going step by step, and our neurons fire in particular ways and so on. And these systems are also doing that. And there's sort of this question of whether the computations that go on in our minds are more sophisticated or not than the computations that go on in systems of random particles bouncing around. And the big point of this principle of computational equivalence is that no, from a sort of zoomed out computational sense, the computations that go on in our minds are no more sophisticated than the computations that go on in systems where they're just, in a sense, particles bouncing around. And that fact is very important for understanding things about nature. Actually, you can go even further than that. A key thing that I've realized in the last few years is that what's really important about this notion of computational irreducibility and this idea that there's computation going on sort of in all these different parts of our universe is that actually our minds are actually limited in the computations they can do. We're quite computationally bounded. We can't trace all of those details of all those computations that are happening in the universe. We can only sample some very compressed version of that. And that fact, the fact that we are computationally bounded, yet what's going on underneath is sort of full computation, unbounded, that interplay turns out, rather excitingly, to lead us to basically the core laws of physics that got discovered in the 20th century, laws about space-time, laws about quantum mechanics, laws about statistical mechanics, and things like the second law of thermodynamics. This is sort of a big story that has been exciting for me in the past few years, is realizing that this fact about us as computationally bounded is what, as compared to the sort of irreducible computation that's happening in the world, that interplay ends up leading us to perceive the laws of physics, natural laws, to be the ways that we have discovered those natural laws to be. So that's a rather long and a bit philosophical response to that question, but it's an interesting question. When does one go from when does one become computational? I think the main answer is as soon as you reach this point of computational equivalence, as soon as you reach the point where running over all these different initial conditions, you would be doing universal computation. That's a sense in which you can say, yes, we've got computation going on there. Now, computation that we can interpret as humans is that's a tiny subset of all the possible computations that can happen. You could define that to be what you mean by computation. I don't think that's terribly useful. I think that's a small subset. And by the way, as we advance, as we build out kind of the things that we understand, we're expanding in this domain of what computations we can consider sort of accessible to human narrative. I mean, the story of my life in the creation of our Wolfram language, computational language, is really a story of defining certain kind of words that represent computational concepts. And as we expand Wolfram language, we're gradually expanding the domain of kind of what that is computational, we can bring into human narrative. We can be able to sort of talk about and write down. Kind of the idea of Wolfram language is to provide this kind of notation for computation that lets one kind of humanize the computation that we care about. You can define in Wolfram language any computation you want, but if you want a short program that is, you have sort of the primitives to do things that are sort of human understandable computation. Actually, I happen to be working on a project right now that is an attempt to understand the extent to which you can or cannot, in a sense, humanize a particular computation that corresponds to a particular long mathematical proof. And it's sort of an interesting case where you say, well, this thing is true. We can see step by step by step by step by step, we get to the result. But can we humanize that? Can we turn it into something where we can, with our sort of finite mathematical minds, expect that we can understand this proof? We can turn it into something where it's sort of explainable, where it isn't just, oh, the computer found that it's true. Look, we can check these 100 million steps and say, yes, it really is true, but that we can really explain, for example, that I could explain to you in some limited amount of time why this result is true. I think that's not going to be possible, but it's an interesting thing to see kind of on the ground that there are things where, yes, the result is quite interesting, but yet there isn't a kind of narrative explanation that is kind of human scaled for it. Let's see. Okay, there are many, many questions here, lots of interesting ones. Brad asks, says their son watched The Matrix for the first time the other night and asked, are we living in the Matrix? How can we know one way or the other? It's an interesting question. It sort of became this idea that somehow we must be living in a simulation because look, we're able to, with our computers and so on, we're able to emulate more and more. We are able to have more and more realistic kind of video games and all this kind of thing. Wouldn't it stand to reason that sort of we are just part of some future entity's video game, so to speak? I have to say that there's a certain strange resonance between this kind of belief, which at least at one time was kind of quite popular in the tech industry, or at least in Silicon Valley. And there's sort of a strange resonance between that and very traditional kind of theological views of, you know, God made the universe and we get to live in it, so to speak. I mean, this relationship and many of the arguments and the kind of discussion about kind of simulation, the kind of the I don't know what you call them. We need a name for the simulators, the folks who are playing the video game in which we are merely players, so to speak. It's some kind of god that is kind of the thing that is the simulator in that setting. But it's kind of strange that god has so much resonance with the kind of the versions of God that exist in many kind of religious traditions and so on. And it's interesting that many of the kind of theological arguments about kind of God and the relationship of God to the universe sort of play also for this God that's doing the simulation. So, for example, one question about sort of the God and the universe, that there are different views. I mean, for example, Spinoza always had this nice quote that the universe is the thoughts of God actualized. But there's really a big question about whether the laws of the universe can they be violated? Can there be miracles that are exceptions to the laws of physics? Or is it the case that the laws of physics, once set up, just do what they do and imply what they imply, which means that in a sense, the God or the God only has that one choice to make. What are the laws of physics that they will set up? Once those laws of physics are set in motion, it's then just a matter of running those laws to find out what will happen. There's no choice. It's kind of like I know I'm trying to remember the exact quotes, but there are questions about, I think Leibniz asked these questions about whether God had a choice in the creation of the universe, so to speak. Well, so that means that in this setting, the God simulator, the best they're going to be able to do, absent miracles, is to decide what are the rules, which will then be set in motion, which will then be our universe. Now, if I remember the Matrix movie, there were some miracles that happened. There were some things that deviated from the mere rules, the computational rules that were supposed to run the universe. Well, in a sense, the evidence for, and it is really a charming thing that this is very much also kind of often quoted in at least some religions as evidence for kind of the existence of God, is there can be miracles which sort of deviate from the laws of physics, which are the kind of the discretionary acts of God, so to speak, independent of the laws of nature as they are set in definite form. Well, I have to say, it's in our model of physics, there's sort of more information here. Because first of all, in our model of physics, there really is a definite identifiable rule that one can imagine that sort of runs the universe. So it really is the case that this thing I've been describing about the God just has to pick the rule and then everything else just runs. But there's more than that. In my current understanding of how physics works and so on, one's really starting from this Rulliad object. The Rulliad is the set of all possible computations, all possible rules that the universe could follow. And the whole point is that we are sampling a tiny part of that space of all possible rules. And not only that, all of us humans are very close together in Rullial space. We're sampling, we all agree on the laws of physics, more or less, because we're really close in Rullial space. We can imagine some alien who's far, far away in Rullial space and has a completely different view about what the laws of physics are. But for us humans, we're all kind of close enough that we agree, just as we're all living on one planet and we kind of all pretty much agree, what does the night sky look like? Because we're all looking at the night sky from one point of view, so to speak. So I think this, with the point of view that what's ultimately there is this Rulliad of all possible computations, then that is a necessary object. There's only one of it. It's unique. Once you have kind of the definition of the idea of rules and computation and so on, you necessarily have the Rulliad. There's profoundly nothing for the God or God to do. What One is the Rulliad is just is the only possibility, so to speak. There's nothing to choose. What there is to choose is where we are in the Rulliad, where in Rullial space we happen to exist. And the very fact that we sort of coherently exist is connected to the fact that we are of a limited size in Rullial space, just as we're of limited size in physical space. If we were kind of dispersed all over the universe, we probably wouldn't think of ourselves as coherently existing as sort of separated entities. And so it is in Rullial space. And I think this notion that we're kind of very localized in Rullial space, but that's, in a sense, we're now, we're taking our simulator is, it's hanging by a very tiny thread. What does it determine? Doesn't determine the Rulliad. The Rulliad necessarily is that way. And then what it's determining is sort of where we are, what we are like. All it could determine is what we are like as observers of the Rulliad. Now, this is where it gets a bit interesting, and I haven't really quite untangled this. The issue is, can you imagine kind of a hierarchy of observers of the Rulliad, so to speak? In other words, we are observers of the Rulliad who have certain characteristics. What does it even mean? The Rulliad has lots and lots of stuff going on in it. We're trying to take all that stuff that's going on and sort of compress it down to just kind of a human, something that fits in the finite minds that we have. So we have to equivalence lots of things. We have to ignore lots of details. And we just have to say, we care about the big picture, about this or that thing happening. And so there is an interesting question of whether the way that equivalencing works, whether one can imagine different sort of levels of how one gets to the kind of equivalencing that we're doing. And perhaps we could say that in a sense it's a different kind of story than, oh, somebody's playing a video game and we're just in it. It's a more complicated story. Let me give you an example of how that story might play out. It's sort of a question of something like take the concept of life. Life on Earth has certain characteristics. It has a great deal of sort of orchestration of molecular processes, and I don't really know fully how to characterize that. I mean, the thing that's really seems to be quite special about life is the way that at the level of individual molecules, it's orchestrating how this or that thing moves around. Whereas most things in chemistry or something like that, it's just like, oh, they're in these molecules, and for all it matters, they're bouncing around randomly. In life, it seems to be the case that it's important that molecules are being transported. Proteins are kind of moving with very specific ways relative to each other at the scale of molecules. It's very computational. It looks very much like a computation. But there's a question of how did we get the particular set of things to fit together in just the way they do to give us life as it is? It really helps to have self-reproduction, because once you have a thing that's working, once you've managed to get that thing that works, has metabolism, whatever else, that operates like life, then you can get to make lots of copies of it. You've sort of replicated that achievement. But this question about sort of how that builds up is not clear, and that relates to questions about the origin of life and so on. And for example, it's quite possible that we are certainly not the first instance of life, or of something like life. If life is defined in terms of this sort of molecular scale orchestration, it could very well have been that there was a life 1.0 that was much simpler, and it provided the environment for life 2.0, 3.0, 4.0. Who knows what serial number we are, what sequence, where we are in the sequence of forms of life, so to speak. Now, it's sort of analogous, I suppose, to what happens in computer systems. There is the raw machine code of a computer system, but the things that we're dealing with, the kind of the windows on our screen, the applications we're running and so on, are many layers up from that underlying machine code. And by the way, in the ways that we have engineered things, it would have been very difficult for us to build everything directly in the machine code. We needed those separate layers of kind of structure to be built: operating systems, Windows systems, user interfaces, networking layers, all this kind of thing. We needed those layers to build up to what we have. So it's sort of, and that's probably the case in building up to something like life. You need these different layers to get to the point where you have this thing where you can build, and it's pretty much the same with computers. You finally build that program, you finally build the Wolfram language binary or something. Once you have it, and it ultimately operates in terms of machine code and so on, but once you have that binary, once you've created that artifact, you can copy that artifact over and over, and you can have that thing achieve those objectives in that way, without having to kind of go back down to the machine code to refigure out how to set that whole thing up. And that's, by the way, the same trick that biological evolution has used. It kind of achieves something, and then it keeps on using that same achievement, so to speak. So I think it sort of remains something of an open question how these kind of layers that get us to being observers like us, how that really works. And is that something where we can imagine that there's kind of a different layer of kind of is there sort of a sublayer, an infra kind of mind that is something which you need to build up to what we actually have. And in a sense, a lot of what we have in sort of the structure of atoms and molecules and chemistry and all that kind of thing, those are, in a sense, those layers. But I don't think this really relates to the usual picture of the sort of God/Ur-God/simulation idea, which is there's something more sophisticated that is simulating something less sophisticated. I don't think that really addresses that issue. And I think that issue, it just doesn't make a lot of sense, because it's something where there just isn't the kind of thing where you might say, hey, I'm being run like a player in a video game. It kind of requires that there be choice on the part of the thing that is playing you. But as I've argued, there really isn't such choice. Let's see. Okay, simple question. It's always a terrible when I say it's a simple question, because those are the ones that are like the potholes that always trip me up. But anyway, Memes asks, is binary the most effective form of computation? Well, first let's explain what that is. When we talk about numbers, we're usually writing numbers in base 10, which means, we have the ones column, the tens column, the hundreds column, et cetera, et cetera, et cetera. Sort of the purer form of numbers that are it's easier to implement in electric circuits is binary, where instead of writing things as ones, tens, hundreds, et cetera, you're writing them as ones, twos, fours, 2 squared, eights, 16s, and so on. You're writing just ones and zeros, and a sequence of ones and zeros are being used to represent numbers. And in a computer memory, it's convenient to just have, well, there's either kind of a bunch of electrons somewhere or there isn't, and that represents either a 1 or a 0. It's like 100,000 electrons represent a 1, and no electrons represents a 0, roughly. It's actually usually not set up quite that way. It's usually set up so that, well, in the end, you sort of balance it so that you're not dealing with, oh, there are electrons or there aren't electrons. It's kind of like there is one pattern of electrons or another pattern of electrons, at least across a series of bits like that. But in any case, that's the way. So for computers, it's just convenient to have sort of the presence or absence of voltage, current, electrons, whatever, represent things. But by the time you've built up to the level of even a machine code, let alone sort of a low-level language or operating system or whatever else, you've long ago kind of abstracted away those issues. And you're really just dealing with, oh, there's a block of bits that represent a number. Now, is it best to represent numbers in the end as ones and zeros? Well, it's been convenient for digital electronics. People have tried doing things like ternary, where you have essentially base 3, but it's usually 1, -1, and 0. And that has some conveniences. There were a bunch of Russian computers, actually, back in the day that used ternary representation. They didn't go fantastically. And I think in the end, by the time you've got all these layers of software built up, the details of what happens at the lowest level really don't matter much. The details of whether you have this instruction or that instruction and that detail or that other detail in the machine code of your computer is just not really relevant. It's just it's a small sort of layer above that, and then you're getting to things which can be sort of the same across all these different machines. Now, the question of whether even representing things in terms of bits is a good way to think about computation, that's an interesting question too. Because usually in a computer, we're storing things at particular locations in memory. The locations in memory of a computer are numbered. And so you can represent them by a number. You say, I've got this location. It's 2,700,000,000, blah, 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 blah. At that location, I'm going to stick this thing that I'm storing, which might be, the pixel on the nose of the cat in the cat image that I have, or something like this, is stuck at that particular location in memory. And those locations in memory are numbered. And so that and those numbers that represent the locations in memory can be represented in binary, et cetera, et cetera, et cetera. So it's a very kind of numbers-oriented way of thinking about things, that you're laying out the memory in sequence, 1, 2, 3, 4, 5, memory locations, so to speak. Is that necessary? Well, no, it isn't. You can imagine quite different ways to do things. For example, neural nets store information in a way that isn't kind of numbered memory locations. It's a big mess, actually. It's the information is stored in these weights of connecting sort of one artificial neuron to another. It's a big tangle of stuff. And there are other cases in which you can think about things in terms not where sort of the lowest level operation does not have to do with things laid out in numerical locations in memory. So, for example, if you're dealing with symbolic expressions, things where, well, you start off with things like an algebraic expression like x plus 1 times x minus 1 or something, but you can generalize that, as we do in Morphin language, to sort of represent any kind of thing, whether it's a chemical or whether it's a piece of graphics or a user interface. All those kinds of things can be represented as symbolic expressions, kind of like a function. The function might be the function that represents, I don't know, a slider, and then that's combined into other things that represent other pieces of user interface. That whole thing, sort of function and arguments of the function, that whole thing is kind of the symbolic representation of pretty much anything you want. And that sort of unification that anything can be represented in that kind of symbolic way, that's a core piece of Morphin language. That's sort of a big idea that I kind of understood back in probably 1979, that you could really represent all these things for sort of human level computation in this symbolic way. But in any case, you can also imagine doing computation just in terms of these symbolic expressions. They're kind of like trees in computer memory. They're not like things where you label 1, 2, 3, 4, 5 location. They're really things that are more like this is connected to that is connected to that. So that's a quite different way to do computation. If you are really into our physics project, the thing that we see as being the underlying infrastructure for everything in the universe, space and everything in it, is hypergraphs, kind of graphs that just say, this is connected to that, or hypergraphs where you can say, this and this and this are all connected, and so on. And in those terms, sort of computation becomes the story of rewriting hypergraphs. If you've got a little piece of graph that looks like this, it's going to get rewritten into a piece of graph that looks like that. You can imagine a sort of infrastructure for computation that has nothing to do with numbers and positions in memory and all those kinds of things. It's a pure story of hypergraphs and the rewriting of hypergraphs. And that's probably how our universe works, or one view of how our universe works. And yes, you can imagine that as well. And in fact, there are a bunch of people and companies that are trying to pursue kind of thinking about computation in terms of hypergraphs, because it's actually a very powerful and very flexible way to be the underlying structure of computation. So really right now, there's the sort of things laid out in numerical positions in memory idea, random access memory, that's typical in most computers. There's kind of the neural network model of computation where it's all these connections and so on. There's the hypergraph model of computation. There's the symbolic expression model of computation. They're all different types of things. What one should build hardware to do is an interesting question. I mean, there's some effort to build hardware that directly emulates neural networks. Biology certainly seems to have things like that, but one can imagine doing that with digital electronics as well. There are efforts to do that kind of thing with symbolic expressions and so on. that's an interesting direction. And it's sort of you end up with a different architecture of computer than the traditional one. And by the way, when people do what they talk about as quantum computing, but we don't have to know about sort of the true sort of many branches of history, quantum mechanics. Instead, we can just think of it as being, well, let's make a computer out of something other than electrons and a semiconductor. Let's make a computer out of, I don't know, cold atoms or something, or let's make a computer out of optical kinds of things with light, things like this. And some of those other sort of models of hardware models of computation lead one maybe to, although it hasn't really been the thrust of what people have done, but some of those things could lead one to sort of different interpretations of what the underlying stuff of computation should be. I mean, there's a class of quantum computers that really have to do with, and I say quantum computers a little bit kind of reluctantly, because I'm not sure that it's not really the quantum aspect of it that I'm emphasizing. It's just the differently physicsed computers, so to speak. But there's a class of those where the idea is that you're trying to set things up so that, well, okay, so if you have a bunch of, I don't know, molecules bouncing around, for example, and you cool them down enough, they become solid, they form a crystal. Well, so that crystal typically has a rather simple structure. The molecules are lined up in a very specific way, but somehow it had to find that way of lining things up. Just as it cooled down, the molecules were bouncing around and they were kind of bumping up against each other. And somehow they found that, oh yeah, if I line up this way, I end up with the lowest energy state. Well, you can set things up so that the thing that you end up finding is the lowest energy state sort of solves a problem. It solves a problem of, well, how do you arrange, sort of how do you get the shortest path from here to there? You can end up with problems like that being encoded in what the lowest energy state of this pattern of objects with certain shapes is. And so that's an example of a kind of a way of doing computation. Just have all these weird shapes and cool them down and see what pattern they form. That's a different form of computation than the traditional one that we have in computers. And it leads to different things being easy, so to speak, to do. And although in the end, this principle of computational equivalence and the whole idea of universal computation tells you that in the end, it's not going to matter. In the end, both of these things are going to be equivalent in the computations they can do, although particular computations may be much more efficient on one than on the other. Let's see. Seeing many interesting questions here, but Eric is asking, do you think we will ever be able to observe a graviton? So, well, let's talk about what gravitons are, first of all. So, one of the things that got discovered around the end of the 19th century, about 120 years ago or so now, was that a lot of things in nature are discrete. So, for example, electricity is, you think about an electric current, you think about sort of say, well, we can have this amount of electric current or that amount of electric current. Well, no, it's not quite right, because in the end, electric current is made of electrons, discrete lumps of electric charge that move from here to there. Well, it also became clear that matter is made of discrete atoms. And then it became clear that you can think of light as being made of discrete particles called photons. And in any given, if you have typical, a light bulb or something, it's spewing out just unbelievable numbers of photons every second. Those photons, kind of the aggregate effect of all those photons can be thought of in different ways. For example, you can think of light as also being like a wave, an electromagnetic wave. That's an alternative to thinking about it as, oh, it's all these photons. And that's a sensible thing to do when you have gazillions of photons, and each individual photon doesn't really do much. It's the aggregate of all those photons that has an effect. Now, as you move down the electromagnetic spectrum to things like X-rays and then gamma rays and so on, the individual photons sort of pack a much bigger punch. And so by the time you're dealing with gamma rays and so on, you're often thinking about individual photons, that individual photon does a bunch of stuff. Okay, so for gravity, it's kind of the same story, that in the effects of gravity that we see them today are very large scale effects. But it's also likely the case that we can think of gravity as being the effect of a huge number of tiny gravitons that are being exchanged between massive objects, just like it's a little bit complicated, but essentially photons get exchanged between charged objects, and gravitons get exchanged between massive objects with mass. So now the question of, can we make a high energy graviton, for example, where we could observe it like we can observe individual photons? The giveaway for photons was a thing called, there were actually a couple of giveaways, but the ultimate giveaway was the photoelectric effect, which was analyzed by Einstein in 1905. And those are ultraviolet photons, photons that have a little bit more energy than the photons in visible light. And what was observed is that they could hit atoms in a metal, and then the atoms would eject one of their electrons. And so it's like photon comes in, electron is ejected. But as far as anybody knew, it was just light comes in and an electron, a discrete electron, is ejected. So you're kind of leveraging the fact that you have one photon, one electron, and that was how things worked. If it hadn't been for the discreteness of the electron, it wouldn't have been easy to tell that there was a discrete photon of light coming in. There was another clue, which was that when you heat an object up, it will emit electromagnetic radiation. That's why things glow: red hot, white hot, blue hot, etc. You're heating it up, and as the atoms are wiggling around, the electrons move around, and that motion produces, just like motion of of electrons in a radio antenna produces a radio wave, so the motion of the electrons in a heated object will produce eventually light, and so on. So it's another clue was a thing called the black body spectrum, which was just what frequencies of light from red to white to blue and so on were produced. And it turned out that there was sort of an easy explanation for the frequencies of light that were produced if you assumed that light came in discrete packets of energy, but not otherwise. So that was sort of another clue. That was from 1900. Max Planck was the person who figured that out, based on work by Ludwig Boltzmann from quite a number of decades earlier. But in any case, so the question is, for gravitons, could we observe something where there's sort of an individual graviton that packs enough of a punch to be able to be observed on its own? Or could there be some collective effect where there is a graviton, where gravitons are interacting with other things, and we can sort of explain graviton, some spectrum of gravitons only in terms of discrete gravitons, a little bit less direct. It's tough. Now, let me talk about a few other things. The other thing is that gravity, we mostly observe it as a static phenomenon. That is that, one planet attracts its moon, or one planet is held in orbit around its star. Those are sort of very static versions of gravity. It's just one thing is pulling on another. But it's also the case that when you wiggle around a massive object, just like when you wiggle around a charged object, it produces electromagnetic radiation like radio waves and so on. When you wiggle around a massive object, the wiggling has to be a bit different than the wiggling that you have for electromagnetism. But when you kind of distort an object, a massive object, it emits gravitational radiation. That wasn't observed. That was observed in around 2015, maybe. Finally, this experiment that I'd seen the precursors of many, many, many years earlier, but a very sensitive experiment, which is kind of observing the deformation of space-time as a result of a gravitational wave going through. Gravitational waves are produced by sort of the wiggling of massive objects. And gravitational waves, that the most effective way to produce gravitational waves is when two black holes merge, or perhaps two neutron stars merge. That produces huge amounts of gravitational radiation, so much gravitational radiation that we can now detect any such merger from pretty much anywhere in the universe. And they happen every week or two, I think. somewhere in the universe, and we get to observe that. But that's gravitational waves. That's the effect of immense numbers of gravitons sort of collectively having this effect on the structure of space-time that we can detect. So now the question is there a way to make sort of a high-energy graviton that we can detect individually? Or is there at least a way of seeing kind of the individual effects of individual gravitons? It's tough. I mean, it's not obvious how you would do that. I will say that things are sort of thrown into another kind of version of complexity by our models of physics, because in our models of physics, space is fundamentally discrete. Space is made of this giant network, and a graviton is something actually very big compared to the discrete structure of space. So we're dealing with the gravitational waves, the static gravitational effects. Those are huge numbers of gravitons. And even the gravitons are huge numbers of elementary atoms of space, so to speak. So we got these different hierarchies, levels of hierarchy. And a thing that I think it may end up being easier to observe the atoms of space than to observe individual gravitons that sort of are pretty big compared to the atoms of space, but still very small compared to things like gravitational waves. Because I think there may be some phenomena that show one the discreteness of space and that are kind of where you can interpret them in terms of some kind of gas of gravitons, but actually it's easier to understand them just in terms of the underlying discrete network that represents space. So I think, well, there are effects that have to do with rapidly spinning black holes. There are effects that are essentially showing that there is sort of discreteness to the way that space-time works that can affect kind of the merger of black holes. When black holes are trying to merge and they're trying to sort of merge the points at the center of black holes, which in our models of physics aren't quite points because they're made of these discrete elements, so to speak. There are features of that will show the difference, I think, I hope, between sort of continuous structure of space and this discrete structure of space. But I don't think gravitons as such come into that really. A graviton is not really defined when it comes to sort of the local discrete structure of space. A graviton, more like a photon, is something where you're sort of packaging up its gravitonness and letting it be transmitted over a large region of space. That's what kind of makes it an independent graviton rather than just a feature of the structure of space. So, there are things that can happen in the very early universe. You can think of sort of a gas of gravitons, but again, it's a little bit close to thinking about the discrete structure of space. And for example, in our models, the dimension of space, which in our experience is 3, in the very early universe, the dimension of space was probably much larger than that. And how that works, and even thinking about what a graviton is like when you're dealing with different dimensionality of space is really quite unclear, at least to me. So it's complicated, and I'm not, if we're really lucky, there will be some clever experiment, like the photoelectric effect ended up being, that will reveal the discreteness of space or will reveal the discreteness of gravity and the existence of gravitons. But exactly what that phenomenon might be, we don't yet know. And most of the very sensitive tests of gravity, not uncommon to find tests of gravity to within 1 part in 1,000 trillion. But those tests of gravity aren't really sensitive to either gravitons or the discrete structure of space. So it's unclear how that will work. Let's see. Let's see, there's Not is asking, is it possible a universe exists that has no equivalent of mass that could be in the same place and time as we are, but are not observable by us? I'm not sure I completely parsed that sentence, but the main thing about mass is it lets you stay in one place. Things like photons and gravitons are massless. They have no mass, and they necessarily travel at the speed of light. They never can get to stay in one place. Not only do they travel at the speed of light, but also time doesn't pass for them. That's the feature of traveling at the speed of light. is that there's no time has elapsed. In terms of our physics project, the way you think about it is all of the sort of computational effort of figuring out what you will do is spent in reassembling yourself at a different place in space, at executing motion. None of it is spent on letting you intrinsically evolve and have an experience of time. So if we were all photons, we would have no experience of time. A photon emitted at the very beginning of the universe will, if it is now absorbed by something, for example, photons from the cosmic microwave background, when we absorb one of those photons, as far as it was concerned, it had just been emitted from the beginning of the universe. No time had passed, and then splat, it's absorbed by some detector that we have for it. But no time had passed internally for it. So the thing that lets time pass internally for us is the fact that we have mass, and we don't travel at the speed of light. We are sort of stuck in one place. Well, we're not quite in one place because the universe is expanding, and we're moving relative to the center of mass of the universe and so on at maybe 1,000th of the speed of light. But you know, we stay in a coherent place, and that's the consequence of the fact that we have mass. The fact that, and that's one feature I haven't fully understood really its significance for us as observers of the universe. The fact that we are observers of the universe who have mass, rather than being massless observers of the universe, just made of photons, for example, is, I think, important. It's important to our notion of time. If we were massless, we would have no notion of time. Now, it's also the case that being massless is kind of hard. Well, photons don't interact with each other. Actually, gravitons do interact with each other, as do gluons, which are also massless particles, although they're massless particles that are confined inside things like protons and so on. So we don't get to see them as kind of separated objects. But those things have, the fact that you're massless doesn't necessarily mean you can't interact, but it does mean that there is, it's sort of, what can I say? No time elapses, but you can have interactions, and you can even have, this gets kind of tricky in particle physics-y, but you can have interactions as a result of the exchange of virtual versions of that same particle, even if the thing is just sort of going along. And this is where it gets tricky, because a graviton, a gluon, a photon, they're all intrinsically massless. When we have them as physical objects that we can kind of detect, they're massless. But for very short periods of time, quantum mechanics and quantum field theory says that there are versions of those particles that do in fact have mass, but they don't exist for very long. And so that's kind of how self-interaction of, for example, gravitons or gluons with each other can happen through virtual gravitons and gluons and so on. That's getting a little bit tricky. So Joseph comments, so I only experienced time because I had mass. Yes, that seems to be true. You would not experience time if you were massless. So it's a feature of, we observe the universe the way we perceive laws of the universe to be the way they are, because we are the way we are. And what characteristics of us are important, we don't fully know yet. Mass is one that's important. It's also important that we are roughly the size we are. We are, I think, if you look at the spectrum from the total size of the universe down to the elementary length, the distance between the atoms of space, we are much more towards the big end than the small end. There's a lot more room down below than there is up above us in terms of scale. Let's see. Harry is asking about dark matter. I think I've talked a little bit about that before, but I'll mention that here. And then maybe we'll go to some slightly different questions. Dark matter was first sort of thought about 100 years ago now, because people were looking at galaxies. Galaxies have been discovered not that long, much earlier, but people were looking at stars and galaxies. And like our galaxy is a spiral galaxy. It has about 100 billion stars in it, and it's rotating. The galaxy is rotating. It rotates, I think, every 150 million years, if I remember correctly. And there are stars that are rotating on the outside. There's stars rotating on the inside. The question is, how much faster do the stars on the outside? Our galaxy has spiral arms, and they're sort of folding in because the stars on the outside are going in their orbits a bit faster than the ones on the inside. So the question is, what is the rotation curve for our galaxy? What's kind of the And you can kind of work it out because you can say, well, the star on the outside is orbiting the stuff in the middle. Once we know what the mass of the stuff in the middle is, we can work out what the orbital period of the stars on the outside are, and so on. And they're very straightforward. Well, Kepler's third law tells us things about the distance, the rotation period, and so on. But those things all assume the usual model of gravity, inverse square law model of gravity. Well, it turns out that rotation curves of galaxies do not quite follow what you would expect based on the mass that we can readily see exists in a galaxy based on stars that we can see, luminous matter, stars that are emitting light, and so on. And so that's led to this notion of dark matter. Maybe there's something in galaxies that's producing mass, but is not visible as something producing light and showing up as a star. What could that dark matter be? My own guess is that it isn't matter at all, that it isn't. People have looked for all kinds of different particles and like mini black holes and all kinds of things that just aren't luminous but have mass. But my guess is that it's actually more likely to be something to do with the structure of space, some feature of some large-scale effect of microscopic features of the structure of space. It's kind of like if you think about heat. People had thought that heat must be a fluid because it flows from one thing to another. That was what was believed in the 1800s. But in fact, we know now that heat is a feature of the microscopic structure of matter. It's the energy with which all those molecules bounce around. Well, my guess is that dark matter is quite likely to be something similar. It's a feature of the microscopic structure of space and not something that's associated with, in the end, with particles and so on. So I think there are various attempts to sort of modify standard gravity, inverse square law gravity, to account for the rotation curves of galaxies. Those haven't technically worked out terribly well. They seem somewhat arbitrary. The big question for our model of physics is, what does it really imply for the rotation curve of a galaxy? That's a tricky thing to work out. It's a big distance from the atoms of space up to the scale of galaxies. And it's pretty hard to work out the consequences over that range of scales. But it's something I'm hoping over the next, it's one of my 2025 resolutions to try and actually see if I can figure that out. It's going to be lots of work, but that's something that I think will be really interesting to see. But I don't know the answer yet. Marcos asked, why do objects in space often take spherical shapes, even though the solar system and galaxies are disks? Well, the reason, what's happening is it's rotation. When things are rotating, they tend to get flattened out. And for example, even if you take a water drop in space, in microgravity, no gravity, a water drop, be it just a big spherical blob. You see that when a water drop is falling in free fall, it's more or less a spherical blob. But if you were able to, which you can do in a space station or something like this, you take this blob of water, you have a big blob of water, you blow on one side, you start it rotating, rotate it faster and faster, it'll elongate. It'll become wider at the equator. Even the Earth is wider at the equator, but not by very much. But you can take a water drop and without it sort of falling under gravity, you can have it, as it spins around, it will elongate in the middle. It's actually a bad idea to do that. If you're actually on a space station, it's kind of not thought to be advisable, because there's a terrible, if you shatter that water drop, you've got lots of little pieces of water that go everywhere, and it's hard to vacuum them up. And I've told that particularly the old Russian Mir space station was just full of little pockets of water all over the place that had happened through the sort of water accidents of various kinds. So not a good idea in practice to do that. But the main physics point is that when you have a rotating thing, it will tend to get elongated. It'll tend to flatten into a disk. And so, for example, when our solar system was formed, there was sort of a protoplanetary disk where it got flattened out. Same reason that galaxies get flattened out. When galaxies are smaller, they are so-called globular clusters, which are more spherical. Our galaxy has a couple, the Magellanic Clouds, that are orbiting our galaxy, and they're more spherical than our galaxy. They're much smaller than our galaxy, maybe I think 1 million stars or so in them. So what tends to happen is gravity without rotation, things become spherical. When there is rotation, things get flattened out. And that's kind of the distinction of when things are flattened versus when things are kind of spherical. It is when you look at things like, well, like planets and so on, they tend not to be rotating terribly fast. And so relative to the sort of the rate of flow of the material that's in them. And stars, likewise, they are elongated. The sun is rotating every few days, I guess, and it is elongated. It's wider at its equator, but not by very much. So that's the basic story with that. And I think in black holes, it's a trickier business. Black holes are often said to have rotation. It's kind of a fake form of rotation. It's really just the configuration of the gravitational field can be explained in terms of two parameters. One is really like mass. It has the effect of what gravity the thing produces at a distance. And the other is kind of like rotation in the sense that with that form of gravitational field, things that are near the object get entrained in the rotation. They get dragged around by that rotation. So it's a little bit kind of like rotation. And in fact, what happens in that case is many aspects of such a rotating, quotes, rotating black hole get incredibly elongated. In fact, when the movie Interstellar was made, my friend Kip Thorne was kind of responsible for the science, and I think the original idea of that movie. But they had, in fact, they were using our Wolfram language and Mathematica to simulate black holes and so on. And they have some black hole in that movie that is a rotating black hole, and it is really flat. The true version of what it sort of would look like, is something incredibly flattened. For the movie, they had to cheat because nobody expects a black hole to be a pancake, so to speak. And so, rather disappointingly, the wonderful simulations of things like the way that light is bent in the gravitational field of such a thing had to be backed off and sort of faked. You know, the physics was actually pretty accurate, and then it had to be made fake inaccurate just to make the black hole actually look like something spherical in the movie. Let's see. Sahil asks, can you share some insights from the work that you and me and my son Christopher did when we worked on the movie Arrival? Gosh, that's so long ago. That must be, when was that? 2016 or something. We got pulled in, Christopher more than I, as kind of science consultants for that movie. It's a movie about alien first contact, and it features kind of the decoding of this alien language. That's a rather interesting alien language. Christopher ended up working on kind of what the actual Wolfram language code that somebody might use to decode that language would be like. And that movie is an incredibly rare, maybe almost unique instance of a case where the code that you see on the screen that is making these sort of analysis pictures is actually the code that made the analysis pictures. That was, much of it was written right kind of on set as the movie was being a few days of the movie being filmed. So that's, but actually this reflects back to the discussion about gravitons, because here's a funny story. So when the movie was in post-production, I get this request, can you make a whiteboard that could appear in the movie? And there were, you know, scientists who were trying to figure out how did these alien spacecraft work and things like this. And it's like, what might those scientists, and I think I had actually suggested that the scientists be Los Alamos scientists, so, you know, American National Lab sort of scientists. What would the typical Los Alamos physicists do when, if confronted with this weird interstellar spacecraft, so to speak? How would they try and analyze what it was doing? What would they guess it was doing? And these spacecraft are a weird shape. You can see that even in the movie poster, so to speak. So I thought, I said, okay, fine, I'll try and do this. So I spent a few hours sort of trying to create this whiteboard, and there was sort of a constraint on the whiteboard, which is don't write in this particular region of the whiteboard, because Amy Adams, who was one of the actors in this movie, is in front of the whiteboard in these scenes. And worst point is she has kind of frizzy hair in the movie. And when you try and composite sort of some background and there's frizzy hair in front, that's tricky to do. So just stay away, just keep that part of the whiteboard white. In the end, I think they sort of the compositing ended up being really hard, and I'm not sure how much of the whiteboard that I ended up writing ended up being used at all. But in any case, I sort of had fun trying to imagine what would the physicists think the kind of the Los Alamos physicists of the 21st century, so to speak, what would they think this weird alien spacecraft with this weird shape and so on, and with certain other characteristics, what would they think it was? And so I sort of had this idea of graviton lasers and the possibility of being able to essentially make a kind of gravitational amplification that could affect the structure of space-time and could allow kind of an alien spacecraft of a weird shape, not to forget, to sort of slide through space-time in some way. So I kind of was trying to make up what somebody might imagine that physics might be like. And so what happens in an ordinary laser is photons have this feature that they like to kind of all get together in the same state. They like to all be exactly the same frequency so that the laser light comes out one color. They like to be all going in the same direction, so the laser light comes out in one direction. They like to, that's a feature of photons, particles like photons, that they like to sort of get together in the same state. Well, the same is true of gravitons. Actually, it's even more interesting with gravitons because whereas photons interact very weakly with other photons, gravitons interact with other gravitons in the way that these things work. The fancy term for this in quantum field theory is that gravity is a non-abelian gauge field theory, which basically just means the things that carry gravitational force also produce gravitational force. Photons, well, electrons have electric charge, but photons don't have electric charge. So electrons can produce photons, but photons don't produce photons because photons are produced by the effects of electric charge, but photons themselves don't have electric charge. Well, actually, photons can produce photons. There's a tiny effect. It's called light-by-light scattering. There's a very tiny effect, which has been observed, where photons can interact with other photons, but it's a very small effect, and it's not the primary. They don't have a basic interaction with each other. They only interact through virtual electron-positron pairs and other complicated things like that. It's a very small effect. But in any case, in the case of gravitons, there is sort of a direct effect. Gravitons can directly interact with other gravitons. Same is true of gluons, actually. Gluons are the carriers of the force that holds quarks together inside things like protons. And actually, in the case of gluons, there's a very direct effect of their self-interaction. If you have an electric charge, it has electric field lines that go out in all directions. And those electric field lines will produce a force of attraction if there's another electric charge that sort of gets into those electric field lines. But because the electric field lines are kind of going out in all directions, the amount of electric of effect goes down like 1 over the area that's the area of the kind of the shell of where those field lines have had to pierce through. And the area of a spherical shell, the area of a sphere is, well, 4 pi r squared. So that means that you're decreasing the sort of amount of electric field that you get at that other point by 1 over r squared, and that's why there's an inverse square law for associated with electric charge, with attraction of electric charges. Well, there's also, when you exchange gluons between quarks, gluons don't have electric charge. Well, I'm sorry, the quarks they have electric charge, but they also have color charge. And the color charge is what gluons are connected to. Gluons are the kind of carriers of the color force, as photons are carriers of sort of electric force. So what happens is that if you just had a quark and the gluons didn't interact with themselves, they just stream outwards just like photons do from an electric charge. But because they do interact with themselves, they all get kind of pulled together. So if you have a quark and another quark, it's got a bunch of sort of gluon field coming out of it. The gluon field doesn't go out in sort of all directions and so have a force that goes down like 1 over r squared. Instead, the gluons, if they're sort of the gluons being exchanged between two quarks, they're all kind of pulled together. So you end up getting this kind of string of gluons between these two quarks. You end up getting something where all of that, there's a flux tube of all of the flux of color of gluons is all kind of concentrated down into this tube. Well, that means you no longer have the effect that as you pull the quarks further apart, you have a lower force of attraction. Instead, the force of attraction actually can go up. It's like a spring pulling it apart as you pull the quarks apart. And that's why we don't get to see quarks, because these quarks get confined inside things like protons. They can't be pulled apart. In fact, if you pull hard enough on the quarks, you'll break that kind of flux tube and you'll form quark-antiquark pairs, and you just get more particles formed that are both quarks and antiquarks bound to each other and so on. So in any case, that's what happens for color charge, and that's how we observe that. Gravitons have a small similar effect. Gravitons, when we exchange gravitons between massive objects, there will be some small tendency for the gravitons to kind of be pulled together. We can't observe that effect. I was asked earlier about whether you can observe individual gravitons. We can't observe those things yet. But and I don't know at what point whether one will come up with a really clever scheme that allows one to observe it. Hasn't been found yet. But in any case, for my kind of science fiction efforts, it was kind of like, well, what if you could have some kind of metamaterial that would sort of would have gravitational effects that would make the graviton self-interaction be important? Then you could use that to essentially make a graviton laser. Once you can make a graviton laser, you'll kind of have these weird effects on spacetime, which I'm not sure what they would be, but I tried to work out in that whiteboard kind of the effect of it, what a graviton laser might be like, and perhaps what effect it would have on the propagation of a spacecraft through spacetime. In any case, it was just science fiction, so to speak. I did describe that whiteboard and in a piece that I wrote about that movie, and somewhat to my amusement, there's at least one, possibly two groups of physicists that have actually kind of worked on things that relate to what's on that whiteboard, which is interesting. I mean, it's an interesting direction in physics. I have to say, I haven't looked and see whether there's sort of an academic citation of the whiteboard and how on earth somebody refers to, whatever it is, the various style guides for how you make a citation in an academic paper. I'm not quite sure how they extend to a whiteboard seen in a fragment in a movie, so to speak. But that's an interesting question. So yeah, there are probably other things to say about that movie, about sort of different forms of language, visual forms of language, different things about kind of ways to interpret, ways to communicate ideas, maybe for another time. I see a question from Mass here. If there's antimatter, is there also antimass? No, there isn't. Antimatter has ordinary mass. Gravity has the same effect on antimatter that it does on ordinary matter. That's something that, well, let's see. There's sort of a fancy quantum field theory version of why that's true, but it isn't really an explanation of why it's true. It's merely a description of the fact that gravitons, assuming it's true, gravitons must have certain characteristics. They have to be spin 2 particles. So But it has been observed, it was first observed, I don't know, what was it, 40, 50 years ago now, that you can get antiprotons and the antiprotons fall under gravity. I think there was a recent experiment that showed even more of that, maybe anti-atoms falling under gravity. It's kind of hard to do the experiment because most of the time when you produce an antiproton along with a proton usually, it's going really fast and it's really difficult to kind of slow it down to the point where you can just, it can have a leisurely sort of falling under Earth gravity, for example, but that has been done and it does indeed fall under gravity. And sort of a reason for that you can think of, I suppose, is that you can think about gravity as being kind of the effect of the curvature of space and the fact that when there is mass in space, it affects kind of how shortest paths go in space. And you can think about that as corresponding to a curvature of space. So you can think, well, the path is always the shortest path. It's just space is curved, so the shortest path is no longer a straight line. And that's kind of the effect of gravity. And in that description, it doesn't really matter whether you have matter or antimatter. It's still going to kind of fall under gravity. I see Harry asking here, can we build a massage chair based on gravitational waves? Well, that's a fun idea. It is true that gravitational waves, when they go through you, they stretch you out in one direction and squash you down in the other direction. Not by very much. The gravitational wave detectors that exist today, LIGO detector, for example, has, so how long is it? Maybe a 2-mile long, has 2 arms. They're both about 2 miles long, and they're in a sort of cross shape. And the distortion when a gravitational wave from a black hole merger on the other side of the universe comes through, the amount of distortion is a small fraction of the radius of an atom. And it's a hard thing to measure, and there's a lot of interesting trickiness in the measurement that's done to be able to measure that. But so it's not a big massage, so to speak. But if you had intense enough gravitational waves, yes, they would sort of distort you in various ways. I would say that by the time you have that intensity of gravitational waves, a lot of very violent things are happening around the universe and the universe around you. And you, as a thing made of atoms, of sort of ordinary atoms held together by forces that are things like covalent bonding forces in chemistry, you don't stand a chance. You will be by the time there are gravitational waves that are seriously massaging you, you're toast. And your forces far greater than those will definitively tear apart all the atoms, probably tear apart you will not be able to exist as a thing that's held together by atomic forces. Let's see, maybe one more question, and I should wrap up for today. Let's see. Gosh. Looking to see if there's anything that I think I can answer in any short period of time here. There's a question from Brianna here. What could the differences in time perception between ourselves, aliens, etc., affect our ability to interact with aliens? And could that be something that accounts for the so-called Fermi paradox? Enrico Fermi was asking kind of like, how come there aren't more intelligent civilizations like ours that we kind of see in the universe? My own view of that, by the way, is that we are at a particular place in physical space. We're also, as I mentioned earlier, at a particular place in rulal space. We view the rules of the universe to be certain rules. And that's a consequence of the fact that we are the way we are. And different minds are in effect at different places in rulal space. And so, the cats and dogs are fairly near us. Things that are other kinds of computational systems in the world of much further away, we don't get to be aligned with sort of thinking about things the same way they think about things. And so the aliens, so to speak, it's easy to have, quotes, intelligent-like behavior, mind-like behavior in the physical world. The difficulty is having mind-like behavior that is close to us in real space and sort of aligned with the way that we think about things. But certainly the question of time is one of those things. I think our notion of time is one where I mentioned, it's related to the fact that we have mass. That's one of the features that leads to a notion of time where time for us, I think, is a sort of irreducible progress of computation. The working out of kind of what we will be like at a successive moment of time is a computational process, and it's an irreducible computational process. So there's one kind of standard of time, which is kind of what a moment of time is, what it takes to do this amount of computation, so to speak. And it doesn't really matter, because of the ideas of universal computation and so on, it doesn't really matter what that computation is. It's just some amount of computation. And you can kind of measure amounts of computation in a way that's not identical for every different way you do the computation, but close enough that you can readily sort of compare them. Kind of a little bit analogous to the absolute scale of temperature. When temperature was first being talked about and people were first imagining thermometers back in the 1600s and so on, it was like a thermometer was something expands as you heat it up. Maybe it's mercury, maybe it's some other alcohol, maybe it's some other fluid, or it's a bar of metal. Something expands as you heat it up, but the amount it expands depends on what it is. But then people realized in the mid-1800s that there could be an absolute scale of temperature that didn't depend on what it was that you were thinking was expanding or whatever with as you increase the temperature. And so it is, I think, with computation. There is an absolute scale of computation that's given to us by the principle of computational equivalence and by sort of measuring irreducible computation. But in any case, that gives us, I think, our notion of time. But certainly there can be, if you're like things like photons, you have no notion of time. Time doesn't pass. If you are, I think it's very important to our form of consciousness that we both believe in the passage of time and believe that we are persistent through the passage of time. It could be the case that we're just a different entity at every successive moment in time. Certainly, we're made of different atoms of space at different moments of time, but yet we feel that it's the same us that carries through those successive moments of time. I mean, this is right now a very sort of philosophical seeming question, but at some moment where, for example, one might be able to upload the human mind into some digital system, or where one's sort of reconstructing a cryonically preserved, human atom by atom or something, and then the question really becomes a lot more real. Is it the same you? For example, if it was the case that an atomic scale copy of you was made, would the thing that was made be the same you? Every, carbon atom is identical. So it isn't the case, even though it was a copied carbon atom, it's not like that was my carbon atom, not the copied carbon atom. They really are the same carbon atom. Yet, and if you could copy things down to a molecular scale, is it the same you or is it not the same you? Now, I think there may be challenges in copying things to a molecular scale that make it difficult to preserve the original while having the copy. And you may end up with something where it is really kind of it's sort of inevitably just one of it. But if you imagine sort of the digital version of the mind, then you have this question again, does as we think about, we're just leading our life, time is passing, then oops, we got copied atom for atom. Are we continuing to lead our life where time is passing? Or is that something different that happened there? So it sort of becomes a more real question when you start thinking about those kinds of things. Is it a continuous thread of time and so on? Now, you can certainly imagine entities for which there isn't a notion that they are persistent in time. I don't really know what those entities will be like, but it's hard for me to even imagine it. But, somebody might say, oh my gosh, you humans just live a finite time. And then for every individual human, it's as if time stops and another human picks up. And it's only the collective of the whole species that persists through time at that point. And you might imagine some entity that would say, gosh, you mean it isn't the same atoms that is you throughout that period of time? You change out your atoms, or maybe you even change out the organism that you are. That's kind of a weird thing. But so, these notions of time and what it is that is the thing that is persistent through time, to say that it is a thing, so to speak, rather than just these different things happening at different times, it's not clear how that will fit together. I mean, another thing I've thought about is kind of how you think about the observer in metamathematical space. If you imagine you have this big structure that is all the different theorems of mathematics proved from each other. One theorem is proved from another, et cetera, et cetera, et cetera. You have this big structure. It has a lot of similarity to the structure of what gets built in space-time. It's another version of this Rouliad object of mine. But the question of sort of how you explore that is a bit different from the way that we progress through time as kind of physical entities. It's sort of more like a mathematician is kind of doing a timeless thing of just sort of selecting theorems that they consider to be true, and sort of doing this thing that is something that exists outside of time. So that's kind of a different story there. All right, I think it's time to wrap up there. So thanks for joining me, and Happy New Year, and look forward to chatting some more in the squared year of 2025. So bye for now.